problem, you probably would be using the pressure-based scheme. But this is what we're going to be using. For now, I'm going to have steady flow, which means that we want a steady flow result. We're not interested in the transient behavior modeling. We're not interested in creating the animation. What happens in the flow behind the airflow. We want the final solution. Now, you should bear in mind that in reality, all these flows are unsteady. There's no such thing as a perfectly steady flow in general. Especially over an airfoil, high alpha. But we're gonna so it's more of a numerical study. The algorithm is going to try to obtain a converged steady flow solution. It's not going to be able to do it. That's what we're going to find out. It's going to have unsteadiness in the way that the fluid is going to be unable to eliminate. And that's just because it's reality. The numerics can't really defeat physical reality. It's a strongly unsteady flow solution. So actually, for the projects, I don't think we've ever done this before in the class. I'm going to recommend that we run transient solutions. I'm going to start off with your study today, but I want you guys to run transient solutions for your final answers for your designs, and actually get a time-dependent solution, and essentially take the average. You're going to graph out what the lift and drag is versus time, and give me an average number. Because that'll be closer to reality. Some of you will have a lot more unsteadiness than others, depends on the specific design. So for now, I'm picking steady. Under models, we don't need any of these things. I don't need the energy equation because I don't have temperature variations to worry about. I don't have heating. I'm going to stick with laminar, not putting turbulence model on for now. So all these things are default. So I haven't changed anything at this point. Materials, the default is the air. Again, I'm not changing the material. Don't mess with cell zone conditions. Boundary conditions is the first thing you need to modify. Go to the airfoil, for example, the first one on the list. And in this case, it may actually be the default. It works. I go under edit and see what specifically it's got set. It's got no slip shear conditions set, which is what we want for the airfoil. Stationary wall, so it's not a turbo machinery or something that's rotating. So leave it alone. Default is fine. For the inflow condition, velocity inflow. What's the velocity that we're going to do? Can we say 18 meters? What? 15. Okay, 15 is all you need to put in there. I don't have any thermal settings or anything. That's all I've got. One setting. Next, outflow. The gauge pressure. Whenever a flow leaves a wind tunnel, it's going to quickly equilibrate with the pressure that's surrounding it, the atmospheric pressure that's outside of the tunnel, which is a gauge pressure of 0. So the default is fine. And as it turns out, the absolute pressure actually doesn't matter at all in a computation like this. The pressure gradients matter, of course. Adverse, favorable pressure gradients, of course, are developing over the airfoil, and those are important. So it does calculate a pressure, but the absolute magnitude of it doesn't matter, only the derivative of it. So that's all we got to do there. We're not doing any adaptation yet. Reference values, important to set. What's the area? I fixed the mesh. We think it's read in English. It's in inches, right? So let's go to scale. Go to mesh, scale, and here, specify. Mesh was created in what? Inches. And then you can press scale, and everything will end up. The grid should be scaled now. What did you do to do that? Yeah, mesh, scale. Mesh was created in, make sure it's in inches. I'm leaving view length unit in meters. You can change this. If you don't like to put it in wasn't inches, it was feet, right? I'm putting the wrong units. It was feet. Let's see, we unscale, I think if I unscale, we have inches. Back to where it was, right? Okay. So we fix this, put it in feet. Scale. Okay, so if I want to view the length units in feet or inches, I can do that. I guess I can go ahead and do that. So my reference values, my reference area is 1. The reference area is the area looking down the airfoil. It should be one foot. So this is showing meters squared. Why is it leaving it meters squared by this? Okay. I think the problem is Fluent does all of its calculations in SI units, and the safest thing to do would be to run would be to do everything in standard SI units. So let's go. We can fix that. Should have changed this. First of all, view length and meters. So what is the area? It's going to be how many meters squared? It's 1 meter in depth from the screen, and the length is 1 foot. 1 foot is how many meters? 0.1 foot is how many meters? 0.3. It's okay. We'll just leave it. You guys can sort it out later. Density, air density of 1.2 at sea level, then that's fine. 0.30 for it. Temperature, velocity got set to 18 or 15 down here. Okay, so the reference conditions are set. These are important because they're going to help. They're going to, when you see the lift and drag coefficient, they'll be appropriate values based on these freeze conditions. This is the plan form area, and these are the freeze conditions it's operating at. Solution method. So we're done with the solution setup. Now we're going to this next category, solution. There's different schemes. We're not going to get into the details of how these work in this class. Maybe at the end we can talk about it. But the Simplec, I would recommend over the Simple. It's got an extra correction step in it to make it more accurate and converge faster. So consider a little more advanced. I would go with Simplec. Usually, to start computations off, I recommend, especially if you're worried about how well your grid's going to perform, is to use first order upwind rather than second order upwind. And what that means is, think of it this way, that numerically it's going to treat the air like it's molasses, like it's got a lot of viscosity. There's going to be a lot of what's called artificial viscosity added. It's not really there, just extra viscosity. And why would you want to do that? Only because it keeps the solution very stable. You get a nice stable development of the flow. Nothing crazy develops. It's not the right answer, but it gets you started. Once you've got that established, then I can turn the second order on, and I get rid of all that that safety net, so to speak. So first order and solution controls. If you run into trouble when you run these things, these are the numbers you're going to want to change. You can lower this 0.7, maybe this 0.3. You don't know what density comes into play here. But pressure and momentum. These are relaxation factors, and the lower you make these numbers, the less the solution will be allowed to change each cycle. As the solution progresses, it makes things more stable. It takes longer though. So if I reduce this to half of its value, it would probably take twice as long to get to the second point. But you'll do it in a more safe way. Once the solution goes, blows up, you've lost it. Monitors. What are we interested in watching? drag monitor. The name is already defaulted as CD1. We could print it to the console and watch it. Just print it to a file. That's what I recommend. What direction is the drag force in? It's in the direction of positive X. Set. Let's do for lift. Same thing, airfoil set. Console. Right. 0, 1, 0 is correct. Okay. All right. So we have those two set. You should also have the moment. Console. Well, the other way. All right to a file. Now, where's the moment center? Usually, if you're going to compare to actual airfoil data, usually it's the quarter chord. So it would be 1/4 of the distance from leading edge to trailing edge, roughly speaking. So in this case, would be what, 1/4 of 0.3. So, 0.75. 0.075, right? Ish. Right. Okay, and the moment axis would be the Z direction. Z out of the plane. All right, so we have those monitors set up. Ready to initialize the solution. You compute that initialization from the inflow conditions. That means it's going to take your inflow conditions of 15 meters per second and just apply that to your whole grid, and that's where the solution is going to start. Okay, press initialize. Which it did.
Good job.
Very fast. The visualization is so fast because the grid's so small. And then we're ready, right? Run calculations. Let's just run one iteration to see if it runs an iteration. It does. See down here, these first, and you guys might want to see the back. Maybe repeat a little more, and then I can show the numbers. Let's take 15 more space. Okay. Now what you're looking at here, these first three columns, these are called the residual. They're the measure of unsteadiness. It's remaining in the solution with respect to the continuity equation, the conservation of mass, and the X momentum, and the Y momentum equations. You remember for fluid mechanics, remember doing control volume analysis? That's really all CFD is, just control volume analysis applied to millions of cells. Taking the kind of the average of the unsteadiness in a given cell, you get these measures. So as this goes towards 0, that means that the solution is completely steady. There's no imbalance of mass at all. If this column drives towards 0, it started off at 1. It's already at 0.038. So it's only got 4% of the unsteadiness that it started with, which is a good sign. The X velocity, Y velocity are already down to really small numbers. And then the lift and drag coefficients here. Look at the lift coefficient, 1.3, drag coefficient of 0.011. That's like a lift drag ratio of, what, 12, 11, 12? Got there. That's not unreasonable. A lift coefficient of above 1 is certainly attainable with an airfoil at high lift, especially an airfoil like this. So I can run this a bit more. Now, you shouldn't get upset if you see that these three columns are not reaching 0 or close enough to 0 for the fluid to stop on its own. That does not mean it's wrong. It just means that there's enough unsteadiness in the solution that it can't get rid of it. That is a measure of unsteadiness, not a measure of how correct it is. And what you're interested in is the lift and the drag in this case. The lift, drag, in the moment. When you see these steady out, you're done. I don't care what these are, where these are. As long as I've got my lift and drag coefficient, is what I'm trying to get, I'm done. In this case. Now I'm going to go ahead and turn on the second order. Well, well, let me not do that just yet. We run this a little longer. See if I get a convergence. So it's not doing. See the residual is going back up for the continuity. Actually having a lot of problems there with the continuity. You can see that. Not a surprise. If you run laminar flow, it's going to be really hard to get any kind of solid convergence. The best thing is to run it out to the point where you see kind of a plateauing behavior or a repeatable behavior. This is what we're up against here. 500. This is 500 iterations, and it's not going to converge, but we can. I think there's a way to bring up the lift and drag districts. Let's see if I can do that. Display plots, maybe files. CL district, for example, almost interesting. Here's the plot history. Here's the lift history. Lift coefficient history up here. So this is a lift coefficient of 1, -1 because I got a downforce. Relative to 1, there's still some pretty strong variation. If you run long enough, you'll see a repeatable. You'll see a repeatable behavior, and that's the best you can do. So I'm going to go back to in an effort to see if I can get a little better result. I'm going to go back to general setup and run transient, run time accurate. Now, when you go to run calculation for time accurate, you got more things to choose. You got to pick the time step you're interested in. 180 to the -3, a microsecond. Doesn't seem like a crazy time step to be looking at. The larger you pick it, actually, the better you might be able to kill the unsteadiness. I think with a really large time step because it's less accurate actually in time. And then if you really want to resolve all the details, true unsteadiness of the flow, you want a smaller time step. So you capture all the flapping of the wake behind the airfoil. If you were interested in doing that. So you want to run 100 time step, let's say for now, and 20 is kind of overkill. Iterations per time step. Rule of thumb is between 10 and 20, depending on the severity of the case. Between 15. Let's see how it does. The question is whether there's a trend, the residual. It's getting a little bit less unsteady. See how the residuals are dropping? Well, they were, but they're coming back up. Did I say that? What I'll do is I'll bring up the same the lift coefficient history too, and you'll see if it's looking any better. We're only ran 100 time steps. version faster per time seller. Notice that. Okay, so I'm going to go ahead and first bring it down. Looks like the same plot we had before, isn't it? Maybe I'm missing something. There was 100 steps, so maybe we just not doing something. Anyway, let me go ahead and save this. Export write case and data file. And I want to read the solution.